So for this example, we're looking for a non-reducing sugar. Non-reducing sugar has either an acetal form or a ketal form at its anomeric carbon. Okay? So what is an acetal and what is a ketal? So if you don't remember, this is a great way to explain this. So an acetal is coming from an aldehyde. So if we use an aldehyde, and we had one equivalent of ethanol, we're going to get something that's called the hemiacetal. The hemiacetal essentially has one equivalent of ethanol as the form of an ether here, and one equivalent of an alcohol on the other side of the molecule. So what this is called a hemiacetal. Okay? Now what if we added two equivalents of ethanol? So we added two equivalents of ethanol. What we're going to form is the acetal. Okay? So notice in this molecule, we still have that hydrogen because that's the key giveaway that this is an aldehyde, but now we just have two equivalents of this ethanol being added. Now we could add any alcohol here, but in this case we use ETOH, and now we're gonna be these dead giveaway here is two ethers at the same connected to the same carbon. Okay, so now we have a ketone. I'm going to show a ketal here. So if we have one equivalent of ethanol, same thing as the acetal, but notice now we have a carbon here instead of a hydrogen. So that's really the difference that's going on here. We have this hydrogen here as opposed to a carbon here. So that's really the only difference. So this is actually called a hemiketal. Okay? Because of the difference of a hydrogen and a carbon here, the R group, if you will be a hydrogen necessarily for an aldehyde, right? Or for a hemiacetal in this case, and the R group for a ketone, or ketal in this case, would be a carbon. Okay? So now if we have ethanol with two equivalents being added, we'll get the fully protected ketone. And notice that the difference between the acetal now and the ketal is this hydrogen in the carbon. Right? The R group has to be necessarily a carbon or some kind of carbon skeleton for the ketal, while the acetal it's a hydrogen. So now we're going to determine which of these is the anomeric carbon. Okay? Some of these compounds could have two different sugars connected to it, so two monosaccharides to form a disaccharide. You could have multiple, essentially you could have a reducing end and a non-reducing end, and it depends. So this question we're just having monosaccharides here. So the anomeric carbon for furanose is located at carbon 2. So if we count the carbons here, we have carbon number 1 here, carbon number 2 right here, which is this guy right here. We have carbon number 3 down here. We have carbon number 4, carbon number 5, carbon number 6. Okay? So now that we know how to number the carbons, we can determine that carbon number 2 for furanose is essentially where the anomeric carbon is located. Now for a pyranose, so I'm going to write that up here. So furanose, anomeric carbon is carbon number 2. Okay? So we have another furanose over here. Notice this is the anomeric carbon at carbon number 1, 2. Okay? And this is another furanose. This is carbon number 1, and this is carbon number 2. So this is the anomeric carbon. Notice this is the carbon on the right side of the molecule. That's essentially the farthest away from that of this CH2OH that's facing up in all of these. Okay? Now this is a pyranose. For a pyranose, we number carbons. So this is in the chair conformation. So this is carbon number 1 right here, carbon number 2, carbon number 3, 4, 5, and carbon number 6. So for a chair conformation of a pyranose or a Hayworth projection, it's at carbon number 1. So this is carbon number 1 right here. So this is the anomeric carbon. So for a pyranose, the anomeric carbon is at carbon number 1. The anomeric carbon is just that one carbon that could form either the beta or the alpha anomer, depending on how it closes, right? Based off of meter rotation. Okay? So now that we have all that identified, let's go to look at this, is this is a reducing sugar or not. So in this case, we have from this carbon, right, from this anomeric carbon, we have a carbon directly connected to it, and we have another carbon, okay? So we have two carbons. So what has two carbons? A ketone has two carbons. So this is coming from a ketone, all right? Once this closes, so before this closed, this came from essentially the linear form of a ketone. So we have 2 carbons. Now, do we have 2 essentially ethers, or do we have an ether and an alcohol? So we have the ether right here, all right, and we have essentially an alcohol right here. So because we have this ether and this alcohol, we know that this must be what's called a hemiketal. So this is the hemiketal right here. Therefore, this cannot possibly be the non-reducing sugar because it has to be an acetal or ketal. So hemiketal is not the correct answer. For this next question right here, let's get rid of this number in here. So we have this carbon right here is connected to a carbon over here, and it's implicit that there's a hydrogen essentially not drawn. So this hydrogen and a carbon, so we know this is coming from an aldehyde. This could be essentially an acetal or hemiacetal. Now we look what we have. So we have an ether here, we have an O connected to some kind of carbons over here, and we have an alcohol right here, so OH. So we know this is coming from the hemiacetal. Therefore, this can open up back into the linear form. This is being so through mutual rotation, these two things are interconverting between the linear form and this chair conformation. So this can't be the answer. This is going to reduce. All right, another example right here. We have this, from this anomeric carbon, we have a carbon. Okay, and we have another carbon right here. This point's a carbon. So we have 2 carbons. This is coming from a ketone. Okay, now is it a ketal or a hemiketal? All right, so we look from this anomeric carbon, we have an oxygen, and we have a carbon attached to this, so this is an ether. And on this other side, we have an OH. All right, so because we have an OH and we have an O, this is coming from a hemiketal. So this, yet again, is considered a reducing sugar. Now, last but not least, we have this anomeric carbon connected to a carbon, connected to another carbon. Right? So this is essentially coming from a ketone as well. Notice this guy, we have a O attached to this anomeric carbon, which is attached to another carbon. So this is coming from an ether. Right? So this is an ether substituent. And this on the other side is an O attached to another carbon. So this is another ether. So this is a fully protected ketal, right? So this is a ketal. And we know that a ketal or an acetal is essentially going to be a non-reducing sugar. So this is the answer. Now, to think about this question a little bit deeper, we can essentially look for alpha and beta anomers here. So the OH at the carbon number 1, carbon number 2 here for a furanose is pointing down, right? And this carbon number 5, right? So carbon 1, 2, 3, 4, 5, this CH2OH substituent is pointing up. So when this carbon number 5 substituent, this CH2OH, is pointing up, and this OH is pointing down, when they're pointing in opposite directions, this is what's called the alpha anomer. So this is an alpha anomer. Okay? In this case right here, we have the OH that's pointing up, and we have this CH2OH that's also pointing up, right? We look at the anomeric carbon, right? And this is pointing up because they're both pointing in the same direction. This is what's called the beta anomer. Okay? Another example, here we have an OH. The OH is pointing up, so this is the carbon number 2 for this furanose. So the carbon number 2's OH is pointing up, and this carbon number 5, right, the CH2OH substituent is also pointing up. So this is up, this is up, this is the beta anomer, okay? And then last but not least, this ketal over here, this guy, this OMe, right, this is pointing down, this is pointing up, right, so carbon number 5's CH2OH substituent is pointing up, and carbon number 2's OMe substituent is pointing down. So this would be the alpha anomer. So for this example, we're looking to form the beta furanose form of L-tagatose. Okay. So what is the furanose form? So furanose form is this 5-membered closed ring because essentially it's coming from a substituent called furan. Okay. So that was something we talked about in class. So in this case, what we want to do is the first step is rotate this 90 degrees such that we have essentially a linear molecule, but now it's horizontal. So we have the CH2OH here on the right, and we have to place the ketone. We can put this facing up or down. It actually doesn't matter, so we can put it this way, or we can face it down. Because of the fact that it's an sp2 hybridized carbon, there is no essentially chirality. So this could be facing either direction. I'll put it down for right now. Now, this OH group, if we rotated this 90 degrees, this would be at the bottom, and hydrogen would be at the top. this other OH would be at the bottom, and this hydrogen would be at the top, okay? Now, where it gets a little difficult is this OH here at this carbon number 5. So I'm going to go ahead and show you how to number this. So we number it from the top. So with the ketone facing the top, that's called the upright position. So this is carbon number 1, carbon number 2, 3, 4, 5, and 6. Now we can look at any of these other sugar options right here from these monosaccharides and number the carbons accordingly. So carbon number 1 would be right here, carbon number 2 would be this one right here, carbon number 3, 4, 5, and carbon number 6. Okay, we can do another example. So this is carbon number 1, 2, 3, 4, 5, and then 6. Carbon 1, 2, 3, 4, 5, 6. And again, 1, 2, 3, 4, 5, 6. Okay. Notice for a furanose, so for ring closing of furanose, the important thing to notice is that the ketone is at carbon 2. So we have a carbon 2 ketone. Okay. And what we have essentially is this carbon 5 oxygen, right, from an OH that's attacking, right? And these two things, that's what's going to essentially form, in all of these cases, the hemiketal, okay? So a hemiketal is being formed. Okay? So to get to the rest of this molecule, what I'm going to do is we're going to have the OH, and we have the CH2OH, okay? So the trick for this is the OH is facing up, okay? So you would draw the OH facing up here, and essentially you would put the CH2OH here off to the side, okay? So, but the trick is you want to essentially draw the CH2OH in the direction that is opposite of where the OH would normally go. So let's give an example. So the OH is typically going to go up, the H to the bottom, and then we can just put the CH2OH over here. So the OH would typically go up because we're rotating this 90 degrees. But if you want to essentially have the correct chiral center at this carbon, this group and this group essentially are going to have to be changed. All of these three, we're going to make two switches, right? Which is essentially the exact same compound. So this carbon, this OH is going to move here, this one's going to move here, and this one's going to move here, okay? The trick though is this is facing left, so the OH is facing here, but in reality the CH2OH group is actually going to go to the opposite direction of where the OH would go. And really what you're doing is you're swapping this group here, this one here, and this hydrogen here, okay? So we can go ahead and copy this and draw this again. So really what we have this second time now is we have the H at the top now, the OH here off to the side, the CH2OH here at the bottom, okay? So now we're ready to ring close. So we take the lone pair from this oxygen, okay? Well, this is carbon number 5, remember? So if we number this, carbon number 1, 2, 3, 4, 5, and then 6, okay? What we do is we take the oxygens, so this OH, the lone pair from the OH at carbon number 5, we attack the ketone, carbon number 2, so that's a schematic for furanose. Now we can start drawing the ring close form. So this is how I would approach it. Go ahead and draw a line depicting this carbon number 3 and carbon number 4 bond, and draw one going up and one going up on the other side. So start essentially forming the furanose form. Okay. So number your carbons so you don't make any mistakes. So this is carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay. So at carbon number 3, the OH is facing down. So in this case, the OH is facing down. Carbon number 4 now, the OH is facing down. So the OH is facing down here. Carbon number 5, because we already did the trick, we already set ourselves up for success. This CH2OH is facing down. If I remind you again of the trick, the OH is facing left, right? So when you want to draw the ring closed form, the CH2OH is going to go in the direction opposite of that of where the OH is supposed to go. So the OH in this case is supposed to go up. So the CH2OH is going to go down. The other way you can think about it is the OH is swapping with the CH2OH, the CH2OH is swapping with the hydrogen, and the hydrogen with the OH, right? Making two swaps is forming the exact same compound. So here at carbon number 5, what we have is the CH2OH going down, and what would have to go up is the hydrogen, which in this case we can just ignore it. I'll draw it for simplicity's sake, but it's being ignored here in the Haworth projection because you don't have to draw the hydrogens. Okay, so this is carbon number 5. Okay, so now we can go ahead and include that oxygen, right? This is the oxygen that's being essentially the nucleophile here. This is attacking the carbonyl carbon 2. So this is carbon number 2 over here. Okay, now we want to form the beta furanose. So this is why we left this carbon, this last part out. So this is the anomeric carbon. Okay, so the anomeric carbon for a beta furanose. So for beta, this carbon number 5, the CH2OH, and this is for a furanose, guys. So CH2OH, but carbon number 5 is in the same direction, pointing in the same direction as essentially carbon number 2, the OH, right, from the anomeric carbon. So if that doesn't make sense, this should hopefully help. So this guy right here, so this CH2OH right here, this guy right there is facing down. So if we want the beta anomer, the OH is also going to have to face down. So let's go ahead and draw that. So we have the OH facing down here. And what else is connected here? We have a CH2OH. So we have the CH2OH facing up. Okay? So this is our beta anomer because we have the OH facing down, the CH2OH facing down. If we wanted to form the alpha anomer for any reason, the OH would now be up and the CH2OH would be down. So if we go ahead and look at our options, we're looking for down and down. So the only option here that matches that is going to be letter B. For this example, we're looking for the compound that will yield the exact same product after catalytic hydrogenation of D-glucose. Okay? So in this example, the D-glucose structure is given, as will be all examples on the exam. What does catalytic hydrogenation mean? That just means reduction. Right? So reduction, essentially we could use 2 different reducing agents. Right? We could use H2 and platinum, or essentially the sodium borohydride in the water. Okay? Both of those would reduce the aldehyde to the primary alcohol. Okay? So how do you perform this reaction? The simplest way of proceeding with this is just literally looking at what the reaction really means. So it's really what it's adding is a hydrogen and a hydrogen, essentially. So if we take this hydrogen and we go to insert it, one hydrogen is going to insert where this CH is in this aldehyde, and the other one's going to insert where the O is. So, easy way to think about this is just add one hydrogen to this CH, and then add one behind the O. So now we have CH2OH, right? We're reducing the aldehyde to the primary alcohol. Okay? So in all of these, let's go ahead and do that. Add a 2, add an H. Add a 2, add an H. 2 and an H. Okay? So after that, we've pretty much, we're almost halfway there to the answer. So how do we know which one of these forms the exact same compound as this guy over here? So first, just inspect them all. So right, right, left, right, left, left, right, left. So this is not the exact same just by looking at it primarily. And actually, none of these will be, right? So none of them have right, right, left, right as any of these combinations. But one of these could possibly be the answer. So how do you draw this? So I'm going to take this compound and redraw it down here. And for all of these examples, this is very similar to the question on your quiz. Essentially what you're looking for is the compound that's been flipped 180 degrees, but is going to form the exact same compound due to the fact there's 2 similar functional groups, the CH2OH at the top and that at the bottom, because it's a symmetrical molecule of some sort, okay? So this is the trick right here. So pay close attention to this. So we take this molecule, okay? And what we do is essentially, we're going to entirely flip it 180 degrees, right? In the plane of the paper. So let's take this guy. I'm going to redraw him over here. And this is going to be the flip version. So in the flip version, what we're about to do is watch very carefully. We're going to take this and rotate it 180 degrees this way. Okay? Notice that now the CH2OH, they're both the same on both sides. I'll redraw them so that it looks a little bit better. But fundamentally, the groups are the same on both sides, so that's why this can occur. Now, this compound is the exact same compound as this one, but it's just been rotated 180 degrees. So that's what this question's asking. So now does this look like any of the options we have? So left, right, left, left. So this is not the answer because neither did this look like the original, nor does it look like this. Left, right, doesn't look like the original, nor does it look like the flip version. Left, right, left, left. This doesn't look like this one either. So this is not the answer. But fortunately, we have one that looks exactly the same. So this is actually going to yield the same product after catalytic hydrogenation as that of D-glucose, D-glucose, right? And then none of them is not going to be an answer, okay? So that's pretty much all there is to this problem. Rotate it 180 degrees, and then essentially look for which one of these is the correct answer. For this problem, we're interested in finding the net charge of cysteine at a pH of 0. Okay, so what does that mean? So the net charges, we're going to be focused on whether this NH3 here, this amine group, is protonated, this SH right here is protonated or deprotonated, and this OH is either protonated or deprotonated. So these corresponding pKa values are going to help us clue us in on that. So for a pH of 0, right, this is very, very acidic. So what we're looking at is if the pH is below that of any of these pKa values, we know that that particular atom in nitrogen, oxygen, or sulfur is going to be protonated. So let's go ahead and write that out. So if we have the pH scale, if we think about this, we have a pH of 0 over here and a pH of 14. Okay, so let's go with this first one. So say we have 10.46. Okay, because the pH is lower, so the number, essentially the pH scale, represents the concentration of H plus in solution. Right, so how much H plus is in solution? How many protons, right? So because 0 is lower than that of 10.46, that means there's sufficient H plus, so there's enough H plus to essentially protonate the amine, this amino group right here, because of the fact that the 0 pH, right, has more H plus, so enough such that it can actually leave this 10.46 protonated, okay? Say we had a pH that was around, say, greater than 10.46. So say we had one around 11. Say we're at 11. Okay, so that means that at 10.46, the pH is lower than that of what we are at. So say we had a pH of 11. Right? At a pH of 11, there would be more OH minus relative to H plus in solution. Therefore, the group would be deprotonated. Okay, because the pH is above that of 10.46. That means it's less acidic, right? So therefore there'd be more base to acid ratio. But in this case, we have a pH of 0. So because it's less than that of the pH of the pKa value for this amino group, there's more H plus rather than OH. So because there's more H plus, this is going to be protonated. So at a pH of 0, this amino group is essentially going to have a plus charge. So this is going to be a charge of +1. Okay? Now this SH group, is the pH lower than that of 8.35? It is, yeah. So it's pH of 0. Because it's pH of 0, what that means is there's going to be enough H plus to protonate this group because the pH is lower than that of the pKa. So when pH is lower than that of pKa, essentially the group is going to be protonated. When the pH is greater than that of the pKa, that means it's going to be deprotonated. Remember that an NH2 group, so NH3, for example, when it's attached to something else, has a plus charge because this is 4 bonds to nitrogen, and nitrogen likes to form 3 bonds, so there's a formal charge of +1. When nitrogen is not bonded to another hydrogen, it just has essentially 3 bonds. It looks like this. It's NH2. So this is considered the deprotonated state. This is considered the protonated state. And the same goes for the other 2 groups. So an SH, right, protonated would be an SH like this. Cannot get another hydrogen, right? So this is not going to form SH2 plus. Neither is the carboxylic acid going to form OH2 plus, right? So the amine will, this carboxylic acid or this SH group, those won't, right? Okay, so we go to the next example. We have a pKa of 10.35. So let's get rid of this stuff. So now we have a pKa of 8.35. So the pKa of 8.35 and a pH of 0, the pH is less than the pKa, therefore this group is protonated because there's more H plus relative to OH minus in solution. So this is +1 as well. But is it really HO +1? That's the question you have to ask yourself. Is this going to get protonated again? And like I just said, it's not. So this is going to have a net charge of 0 because of the fact that this SH group is not going to pick up an additional hydrogen, and it's not going to form SH2+, right? It's only going to form this at the maximum. The deprotonated state would have S with the minus sign. So I'll go ahead and draw that over here. So SH, this is the protonated form, and then S minus is the deprotonated form. Okay? Think of that as like an alcohol of some sort. Okay? So for this last group, this carboxylic acid, we have a pK of 1.92. So go ahead and reset this. So at a pK of 1.92, the pH is still very low. So the pH is still at 0. The pK is at 1.92. So pH is less than pK, therefore the group is protonated. Protonated carboxylic acid looks like this. The deprotonated carboxylic acid is what's called a carboxylate, and this would be present when the pH would be greater than the pK, but in this case it's not. So this group, this would not pick up another hydrogen, so this is going to be essentially what it's going to look like at this pH of 0. So this has 0 charge, this has 0 charge, this is a +1 charge. So the corresponding pK values are provided so you can find what the charge is going to be at this pH. And the net charge overall, you add +1 plus 0 plus 0, which is an overall charge of +1. So for this final example, I'm going to show you the ring closure for a pyranose from a 6-carbon aldohexose, okay? So we're looking to form the pyranose. And as well, I'm going to show you the pyranose form as that of a Haworth or Haworth projection. And I'm going to show you as the chair conformation. So we're going to take it a step further on this one. So the first step of this, guys, is the same what you do as the pyranose. You rotate this 90 degrees, okay? So go ahead and draw this line horizontally. The aldehyde goes at the end, so you can either draw the aldehyde or just write CHO. I'm going to go ahead and draw the aldehyde, and I'm going to put this carbonyl down. You can put it up, it does not matter because this carbon is sp2 hybridized, so it does not have chirality. This OH is going to be facing up because we rotated this 90 degrees to the right. This other OH is also going to be up due to the rotation 90 degrees to the right. This OH is going to be down. The hydrogen would be up. And this last carbon we'll have to talk about because there's a little trick you have to use. So let's number these carbons. So it starts from the aldehyde because this compound in the upright position has the aldehyde at the top and it has the primary alcohol at the bottom. So we have carbon number 1, carbon number 2, 3, 4, 5, carbon number 6. Okay? So if we number these carbons on this sideways kind of linear form, we have 1, 2, 3, 4. Now we need to talk about this last carbon. So what are we going to do with this? So, like I talked about the pyranose, when the OH group in the CH2O group at this carbon 5 and carbon 6, we have to use a special way of kind of treating this so that we get the right chirality. So in this example, the OH is on the right. So when we drew this, rotating in 90 degrees, the OH would want to go down. Okay? So it's like the OH goes down, the H goes up, and this CH2OH is hanging here at the end. Okay? The trick is that you need to make essentially 2 swaps to get the same molecule, but you want this CH2OH to be one of the chiral centers and you want the OH to be at the end. So how would you accomplish this? You rotate this way this time, right? Okay? So if we go ahead and draw this again, now I can show you what it's going to look like. So get rid of these arrows and we can go ahead and draw the groups as they would be. So let's go ahead and draw these substitutions. So the H now is at the bottom. The OH is now over here. CH2 group, OH group is over here. So here's CH2OH. Okay? So another way to think about this is the OH is going down, therefore the CH2OH is going to take the opposite location as that of where the OH was supposed to be going. Right? So the OH is supposed to be going down because this is being rotated 90 degrees to the right. So because it's supposed to be going down, this CH2OH would be going up. Another trick is for D sugars, the CH2OH group is going to be facing up always because this is always going to be on the right. And for L sugars, the CH2OH group would always be facing down like we saw earlier because essentially the OH would be on the left. And when the OH at carbon number 5, right, so think of this as carbon number 5 and this CH2OH group here, carbon number 6, right? The OH group, when we rotated this molecule 90 degrees to the right, the OH would go up, therefore CH2OH would go down, okay? So now that we have this thing oriented, we can go ahead and take the lone pair from this oxygen here at carbon number, so we can go ahead and finish numbering this, so carbon number 5, carbon number 6, so it's the OH at carbon number 5. This is going to go ahead and attack the aldehyde at carbon number 1, okay? It'll kick up an electron to the O. We don't have to show this right now, we're just looking to close this. So if we just notice what we did, we have for pyranose formation, we essentially take so we have carbon number 1, in this case we have an aldehyde, and we have a carbon number 5, we have the OH with the lone pair. So it's fundamentally the lone pair that's acting like a nucleophile here, okay? So essentially the carbon number 5's OH attacks the carbon number 1, the aldehyde, right? And that's what's going to form this 6-membered ring called a pyranose. So now we can go ahead and get to work. So we have a pyranose form. So I'm going to show you what a generic pyranose is going to look like. Okay, so it's going to look like this. And this would be carbon number 2. This would be carbon number 3, 4, 5. So let me go ahead and number that. So I numbered it using a different method. So let's go ahead and do this. This is carbon number 1, 2, 3, 4, 5. And this is 6. So there's going to be another carbon over here. So I'm just going to label this as CH2OH in this case. This is carbon number 6. So this is just a generic template for a D sugars pyranose form. Okay, so let's go ahead and make the D mannose pyranose form. So let's go ahead and draw a line at the bottom. Draw a line coming up. Draw a line coming up. Let's number these carbons. So this is going to be number 2. This is going to be carbon number 3. This is carbon number 4. Okay. And I'm going to keep bringing this up. So this is carbon number 5. We have the O over here, and we have this. So we have carbon number 5 right here, and carbon number 6 is going to be hanging out over here. So we'll add that later. Okay. So now at carbon number 2, we literally copy this. So OH is facing up. Therefore, OH is facing up. At carbon number 3, OH is also facing up. Therefore, OH is facing up here. Okay. Carbon number 4 right here. It's carbon number 4. The OH is facing down. Therefore, the OH is facing down here as well. We don't have to draw the hydrogens right now just because on the exam they're not going to be provided most of the time. So actually I'm just going to make this line shorter and we're just going to draw it like that. So OH is facing down. Now carbon number 5, we have the CH2OH facing up because of that little trick we did. All right, and I'll remind you again that the trick is OH is facing right. Therefore, the CH2OH takes the direction of the opposite of where the OH is supposed to go. So the OH is supposed to go down when you rotate this 90 degrees. Therefore, CH2OH is going to be facing up after you do this 2-group switch. Okay? For an L sugar, because the OH is on the left, therefore the CH2OH group is always going to be facing down as opposed to facing up. Okay? So this is practically completed at this point. All we have to do is essentially focus on the anomeric carbon now. So we have carbon number 1 over here. So in this case, say we want to form the beta anomer. So let's go ahead and form the beta anomer. So for beta anomer, the OH group is going to be facing in the same direction as that of the CH2OH group. Okay. So in this guy, this group right here, now in purple, is going to be facing in the same direction as that of this OH that I drew as true in purple. So this right here is what's called the beta anomer. So this is beta. And now if we want to draw the alpha anomer, we would literally copy the exact same molecule. However, now you're going to change this anomeric carbon. So the anomeric carbon for a pyranose is at carbon number 1. So this is going to be facing down. So now this is what's called the alpha anomer because this group is facing up and this group is facing down. So this carbon number 5 CH2OH is facing up. The carbon number 1's OH is facing down. For a beta anomer, the carbon number 5 CH2OH group is facing up, and as well as the carbon number 1's OH group is also facing up. So this is the beta anomer, and this is the alpha anomer for D-mannose. Okay? Now, sometimes on the exam, you may have to convert these two structures into chair forms. Okay? So I'm going to make some room over here, and let's go ahead and show the chair form. So, to draw a chair, essentially what you're looking to do is you're going to draw this skeleton first. And these questions will be multiple choice on the exam, so you will never have to draw one of these per se. So, when we essentially form the Pyranose form and we want to go to the chair Pyranose, right, the carbon is essentially like this. So we number carbons. This is going to be carbon number 1. This is carbon number 2, carbon number 3, carbon number 4, 5, and then there's going to be a carbon number 6 coming out over here from the CH2OH. But that's all we need for right now. So, say we want to form the beta anomer of this guy, right? So for beta, this group is facing up, this group's facing up, and this group's facing up. So let's go ahead and install these groups. So the anomeric carbon, carbon number 1, if this is facing up, this group's facing up. So first I'm going to do a quick crash course on the axial versus equatorial positions of the chair conformation. So for axial, groups are essentially facing such that they're facing up or down. So axial is down in this position, up in this position, down in this position, up at carbon number 4 like this, down at carbon number 5, right? And in theory, you would have another position at this carbon number 6, but this is now a ring with a 6-membered as the oxygen. So these blue guys are axial, okay? Now for equatorial positions kind of follow the contours of the molecule. So this could be an equatorial OH, this could be an equatorial OH, right? It follows the plane of the molecule going this way. This could be an OH this way, follows the plane of the molecule, OH going this way, equatorial, and this could also be going this way, right? Following the plane of the molecule. So the equatorial are now these orange, right? So equatorial, in this case, is up at this position, right? It's up relative to this guy being down. So this position, axial is down, equatorial is up. At this carbon number 2, right, axial is up, equatorial is down, right? It just means that this carbon is facing up while the hydrogen is facing down. Therefore, this would be essentially an axial position, or this would be an equatorial, right? So here is reversed again, right? Axial is facing down, equatorial is up. Here, equatorial is down, axial is up. Here, essentially, the equatorial is up and the axial is down. Okay? So now that we just reviewed that, let's go ahead and get rid of all this, and we're going to go ahead and fill out the actual structure for the beta D mannose in the chair form. Okay? So we're going to start with this anomeric carbon. For the anomeric carbon, we notice that this is facing up. Therefore, we take what was the up form here, which is the equatorial position. For carbon number 2, we have facing up as well. So we take the up. So up would be the axial position, down would be the equatorial. So we need the up position. So in this case, we're going to have up. Okay. In this case, at carbon number 3, we're also facing up. So up is the equatorial, down is the axial. So we take the axial position, the equatorial position. So equatorial is facing up. Carbon number 4 is facing down. So at carbon number 4, we have down equatorial, up axial. So essentially we take the equatorial position, so it's facing down. And then at carbon number 5, we're facing up. The hydrogen is facing down, right? This implicitly drawn hydrogen here is facing down. So this group is going to be taking the equatorial as well, as opposed to the axial. So this is CH2OH. Okay? So this right here, this is what's called the beta anomer. Okay? So another way of drawing this, so this is the beta anomer for a chair conformation. So if we copy this over and we do this again, we can actually find the alpha anomer pretty simply. So let's go ahead and fix this up. So the alpha anomer is really just a swap of this. So we have the alpha here, which is actually facing down. So at carbon number 1, all we have to do is change this, because we know that up is equatorial at this carbon number 1, and down is axial. So because down is axial, we're looking for the down, this is where essentially the anomer for the alpha is going to form. So the alpha anomer is going to have this carbon, this OH down at carbon number 1, while the beta anomer is going to have the OH facing up at carbon number 1. So that's basically all you have to do to change between the Pyrenees form into the Hayworth and then into the chair. So you can interconvert between all of these forms because this is a reducing sugar because it forms a hemiacetal.